Good day, ladies and gentlemen. My name is Bodo Randolph, and on today's lesson, I'll be taking you through the Laplacian. So, when you talk about the Laplacian is just the divergence of the gradient of a vector field, and the Laplacian operator is given by delta square, which is equal to this operator. So, the Laplacian operator is given as this particular equation here. So one thing you have to note is that with Laplacian, we can find the Laplacian of a scalar. When you find the Laplacian of a scalar, it gives us a scalar. We can also find the Laplacian of a vector. When you find the Laplacian of a vector, it gives us a vector. So we'll be illustrating this with examples. So first of all, we will learn how to find the Laplacian of a scalar field, which we are supposed to end up with a scalar. So let's just take this scalar field f of x, y, z equals xy squared plus z cubed. We are supposed to find the Laplacian of this particular scalar field. So the Laplacian of this scalar field will give us del squared del x squared, everything here. So we also have this, and we also have this. So when you do this differentiation twice, you are going to end up with 2y. Sorry. So when you do this first, you're going to get just y squared plus z squared. So this is going to give you 0. Then when you do this one is going to give you 2x. Then when you do this one is going to give you plus 6c. So that means that the Laplacian of this particular scalar field will give us 2x plus 6z. And you realize that we have something which is also scalar. So when you find the Laplacian of a scalar field, we end up getting a scalar. So now let's see when we have a vector field. So we're going to illustrate that one with this particular example. We're supposed to find Laplacian of this vector field. So we have xzi minus y squared j, then plus 2x squared y k. So when you take the Laplacian operator through, you know the Laplacian operator is a linear operator. So you can take it through and you get the Laplacian of xc I minus the Laplacian of y squared j plus Laplacian of 2x squared y k. So now we have three different scalars that you are supposed to find the Laplacian of. So when you take the first one, Laplacian of xz, this will be equal to del squared xz over del x squared plus del squared sz over del y squared plus del squared del z squared over xz. So you realize that when you do this differentiation, we get 0. This gives us 0, and this also gives us 0. So that means everything here gives us 0. When we do the second one, so with the second one, we had the Laplacian of y squared. So you realize that this will give us del square del s square of y squared. We get this, and we also get this. So you realize that When you do this, this gives you 0, this gives you 2y and 2. So we have 2 here and we get 0. So this particular differentiation, we get 2 for it. Then when you go to the last one, so with the last one, we have 2x squared y. So you realize that this will give us, and we also have, this also gives us. So when you do this particular differentiation, know that you are going to end up with 4y. This gives you 0 and this gives you 0. So realize that the Laplacian of our scalar field, sorry, our vector field, was equal to the Laplacian of the first one, I, which gives us 0, minus the Laplacian of the second one, j, which gives us 2, and plus the Laplacian of the last one, k. So that means that the Laplacian of this vector field is minus 2j plus 4yk. You see, when you found the Laplacian of the vector field, we ended up with a vector field. So that's it on Laplacian. Thank you.